Welcome student in our today's online section of subject mechatronics. Today we are going to discuss the another concept of this topic, which is frequency domain analysis. This time domain analysis numerical I will teach you in the next section. Today we are going to discuss this frequency domain analysis. I want to inform you that this frequency domain analysis is asked very few times in the in examination. Actually, this is the tricky part in which the Bode's plot is also included, but this asks very few times in the examination. That's why we just going to take an introduction of them. We are not going to study it in brief. Okay, so here we are. The frequency domain analysis of a system is defined as the steady state response of the system to a sinusoidal input signal. So whenever we are having this sinusoidal input and we are getting this steady state output, you know what is the steady state output? It is the output where the value of this output is not changing more than the 2%. We already teach initially we are having transient response, then we are having the steady state response. So to study the steady state response, we are going to study the frequency domain analysis. The sinusoid is a unique input signal and the resulting output signal for a linear system as well as signal throughout the system is a sinusoidal in the steady state. Output differs from the input only in amplitude and phase. So here it is the input and it is the output. Output is firstly it is transient response, then it is a steady state. You know, transient response means it is continuously changing with time, but steady state response, it is a steady one where it is not going to be differ more than the 2%. So on the output and input are difference only in the amplitude. Here it is the amplitude and it is the phase. Phase means it is the difference between the points where the response wave or sine waves interacts with the horizontal axis. Now this frequency domain analysis of a system, in it the frequency domain analysis is a better option with respect to the higher order system. The time response of a higher order system is difficult to determine analytically. Frequency domain analysis is a better suited when it comes to determine sensitivity of a system to a uncertainty, means the parameter process and variation in mechanical and electrical noises. Frequency domain analysis is better suited when it comes to accessing relative stability of a system. Then here it is simply a frequency domain analysis of a system. Input applied is some form which is sine wave, which is sinusoidal form r of t is equals to a into sine of omega t, and the output which we are going to get there is y of t is equals to y into sine of omega t plus phi. Here phi is the phase change and this omega t will be the amplitude. Omega is the frequency of the sine wave and y is the magnitude of output and this phi is the phase shift. Here only difference between these is to amplitude and the phase shift. So here we are. So in these two above equations, A is the amplitude of the sine wave and omega is the frequency. The difference is only in the amplitude. A is changing here by y and phase shift is added to the output here. Now here it is an important part. The frequency domain analysis using a Bode's plot. So Bode's plot, it is a plot using which we are going to do the frequency analysis. Before this, listen me. In a frequency response analysis of a control system, the steady state response of a system to a sinusoidal input is of interest. The frequency response analysis are carried out in the frequency domain rather than the time domain. Here if we are considering it r of t into a into sine of omega t, if here we are going to replace this okay, so for this frequency analysis we are going to replace this variable. We are taking to the Laplace variable s can be replaced by j omega to convert transfer function into a frequency domain analysis. So to get this frequency domain analysis, simply we are going to replace the Laplace transfer function or Laplace variable s by j of w. Okay, so here we are having this Bode plot. So Bode plot is normally performed to do the frequency analysis. So in Bode plot you can see here there are two different graphs. First one is the magnitude against frequency and second one is the phase against frequency. These two graphs are plots here, and these are the various system performance which we are going to study. So we are going to see this in the next. So listen me. A Bode plot is a useful tool that shows the gain and phase response of a system control for a different frequency. So here it shows us the gain over the frequency. Frequency is plotted on the x-axis. Bode plot are used to show Fourier transfer of a given control system. On Bode's plot, frequency is plotted on the logarithmic frequency axis. So it is the frequency is plotted on the logarithmic frequency axis. The length of decay decreases as you move toward the right of the graph. In Bode's plot, magnitude is shown in the decibel unit and the Bode's plot phase shown in the degree unit. So here this phase is shown in the degree unit and the magnitude is shown in the decibel unit. The most useful way to display the function is with the two plots, the first showing the magnitude of the transfer function and second showing its phase. It is the magnitude against frequency and next one is the phase against frequency. So here we are having some rules to draw this Bode plot here. So here you can see on this first condition, when we are having a constant k, means we are having a simple transfer function which is equals to 20 into log base 10 of k. At that time, how the Bode's plot will be constructed? Here you can see it is the magnitude which is having 20, so we are drawing a 20 straight line for the magnitude against frequency, and for this phase we are having this here ranges which k is greater than 0 is equals to 0, or when k is less than 0 is equals to plus minus 180. So here we are going to draw this straight line on the frequency. For this student, listen me, they are not going to ask us to draw this Bode's plot. Here we are having only the introduction, so no need to much more worry about that. For rule number 2, when we are having a pole such as 1 upon s upon omega plus 1, so after having the transfer function, here we are going to find out the pole. How we are going to find out the pole? By taking the Laplace transfer of this denominator and then equate with it 0, and then we will get the pole, and the value of pole is 1 upon s upon omega plus 1. So here this lower frequency asymptote at 0 decibel, then high frequency asymptote is at minus 20 degree decibel. So whenever we are having the real pole like this, then these conditions we need to be considered. Then connect asymptotic lines at omega 0. Here you can see this low frequency is 0 and high frequency is minus 20 decibels. So 0 and this is the decibels are showing. Then low frequency asymptote at 0 degree, then high frequency asymptote at minus 90 degree. So in this case we are getting this Bode plot are like this in the manner. So when we are having this real 0, you know how we are going to get the 0. We are getting the 0 by taking the equating the Laplace transfer of the numerator of the transfer function to 0. So here we are getting this lower frequency asymptote as 0 decibel. Here you can see the 0 decibel. We are getting this lower. Then higher frequency asymptote as plus 20 decibel per decibel. Then connect asymptote line at omega 0. The low frequency asymptote at 0, then higher frequency asymptote at plus 90 degree, and connect with the line from minus 0.1 omega 0 to 10 omega 0. So these are the types of graph we will get when we are having the value of real 0 as s upon omega 0 plus 1. Similarly, these are the rules when we are getting the value of pole as 1 upon s. We will get these graphs like this, you can see on your screen. When we are having the 0 at origin s, then at that time the graphs are like this, you can see on your screen. Then these are the frequency domain specification. So here the resonance peak, it is the maximum value of the magnitude. You know what is the magnitude and all these of the sine wave here. Then m of r, or resonance peak, gives indications on the relative stability of a stable closed loop system. Normally a large resonance peak corresponds to a large maximum overshoot of the step response for the most control system. It is generally accepted in the practice that the desired value of m of r should be between 1.1 and 1.5. The resonant frequency is the frequency at which the peak resonance m of r occurs. Then here is the bandwidth definition. Bandwidth, it is the frequency range over which the magnitude drops 3 decibels from its zero frequency value. Bandwidth gives the indications of the transient response properties in time domain. A large bandwidth corresponds to a faster rise time. Then here are the gain and phase margin from the Bode plot. So simply knowing that the system is stable is not enough. Important is to assess the relative stability. The stability margin helps in assessing the relative stability. So here is the gain margin. It is a factor by which the system gain can be increased before the system becomes unstable in closed loop. So gain margin should be greater than 1 for the system to stable in a closed loop. Gain margin is determined at a phase crossover. Then we are having the phase margin. It is the amount by which the phase exists 180 degree. A phase margin should be greater than 0 for a system to be stable in a closed loop. Phase margin is determined as the gain crossover. Then estimate, normally we can estimate the transfer function from the Bode plot. Here we are going to study the theory only, we will not have its numerical. So step 1 of this, order of the system. The final value of the phase speaks about the order. So initially we need to take the arrange the order of in this equation. Then if the final value of the phase is minus 90 degree, then it means that there is one extra pole compared to the 0. Then step 2, number of poles and 0. From the magnitude plot, determine the shift in a slope. If the initial slope is minus 20 decibel per degree and the final slope is minus 40 dB by then it means that there are 2 poles and no zeros. The step 3 is of location of poles and 0. If the poles and zeros are at origin, they will pass 0 decibel at 1 rad per second. If the poles upon zeros are real, determine the location of frequency at which the plot breaks away. Then step 4 is of gain. From the max gain determined from magnitude plot, subtract gain from the poles or zeros. Then equate this value to the formula 20 log base 10 of k and determine the value of k, which will be our transfer function. Okay, so this is the frequency domain analysis. It asks very rarely in the exam. After this we will study about the frequency domain analysis. We will study about some types of the frequencies. The frequencies such as natural frequency, then damping frequency, damping ratio, and damp natural frequency. I will teach you these types of frequency in the next section. Okay, so today we are stopping here and see you in the next section soon. Thank you.